There, kids.
It's 3.4 notes, properties of logarithmic functions. These are some really handy properties.
Handy indeed.
And they have to do with the rules that we have with exponents. So
yes.
Can I go over those
real
quick?
Yes, please. Let's just touch some bases with those exponential rules.
So I'm just going to use a generic letter A and some generic other letters. Let me start that letter over. Okay, if I have A to the M times A to the N, remember that we can add those exponents together because of the fact they have the same base. We can just add the exponents together. So this would be a case like where you have x squared times x to the third equals x to the fifth.
Right, because 2 plus 3.
Yeah, yes. and that's the product rule. The quotient
The pro rule. Is this going to be the quo? The pro quo.
Is that if we have them being divided, instead of adding the exponents together, we subtract them. And so that's like where you cancel things out, right? Like x to the 6th over x to the 4th is
x squared.
X squared. And then the power rule.
I've got the power.
Yeah, exactly. The power rule.
You probably don't even remember that song.
No, well, remember it? Probably not. I know the song. Yeah. Is where you have something and then it's raised to a power. And so you multiply those two things together. Okay,
there you go.
So those are our exponent rules, and they are connected to these logarithmic rules because logarithms and exponential functions are related.
They're inverses.
They are.
They're inverses,
yeah,
Steve 320.
That's so true. So if you have two things inside of this parentheses for your logarithm that are being multiplied together, you can separate those into two different logarithms where you add them together.
Right.
So you have to remember that multiplication and addition go together for this rule.
Right. And multiplication and addition go together anyway.
Yeah, in general, those things should make sense that they go together. If we are dividing R divided by S, we can split those into subtraction.
Because oftentimes division and subtraction go together.
Yes, they do.
Yes, indeed.
And this says R to the C. It looks a little funny, but that's like R raised to the C power. Yeah. What you can do is you can move that in front of what you've got going on there.
Right. So now that is a little bit of a trickeration rule. That's not one that we would normally think of.
Yeah, I don't know. To me, it just makes sense because like if I've got maybe this situation going on, I just think of it like that exponent's not really attached, so it gets to float up in front or something like that. Right. But however you need to think about it is fine. We're going to prove one of these.
Oh, my goodness.
What did you do to my colors?
Okay, choose crayons. Choose, no, to the right.
Oh.
Right there.
Okay. My crayons were gone. Okay, so we're going to prove the product rule. So here's what we're going to do. We're going to start with a little bit of substitution. Now,
how come we're substituting right off the bat?
Because that's what we're supposed to do.
Okay, if you say so. I believe you.
I'm gonna be on. Can I be real right now?
Yeah.
Okay.
Are you imaginary?
No. Maybe. Ow, that hurt. Don't do that.
You felt real.
Don't do that. Okay, so I found this proof tricky. I actually had to look it up. And so this is not something we would expect you to do on your own. But it is kind of interesting to see, well, why is it that this is really true? How do we know that this is true?
Let's do it. Is this part of your master's work that you came across this? Highfalutin mathematical
No, I looked it up
proof?
In our book.
Oh, it's in the book?
Yeah.
Did you Google it?
No, it's in our book.
Okay, all right.
Okay.
Did you find it on Bing? Did you use Wolfram Alpha? You're going to ignore me now for the rest of this video? It's going to be a long time.
Actually, I don't think it will be. If it is, it's your fault. We're going to make this substitution. We're going to think about, let's let x be this first part. Let's let y be the second part.
And that's a good idea because those are different numbers.
Yeah, those are two different things. So we're going to let them equal separate things. And then we're going to think about what that means R times S would be.
Okay.
If we have R times S, no, I'm sorry, I skipped a step. Let's change these to exponential functions. So that would be b to the x equals r.
Right.
And b to the y equals s.
Right, because a logarithm is equal to its exponent. So if the base has to be b, then the equals part is the exponent.
Right. So now let's look at r times s. Because at some point, that's where we kind of need to get to. We need to get back to what is this that we're trying to show.
So R times S, we want to show an equality statement with this. So we would want to actually show what R times S would be.
Right. So R is B to the X, S is B to the Y. So let's multiply those together.
Since the bases are the same, I bet you add exponents. I'm just saying.
That is this product rule for things. So that's X plus Y. And that's still what R times S is? Oh, that's not an S.
That's the weirdest S I ever seen.
Okay, so now we want to continue trying to get this. So we're going to take the log base B of both sides of our equation.
Well, I have a log base B. Whoa. Okay, all right.
Okay, and that's something that we will talk about, especially in the next section when we're solving equations, that in order to get rid of this B on the right side, if we take the log base B of both sides, kind of like if you take the square root of both sides or things like that, you know. Oh, look at this property from 3.3 that shows up, the one where these are next to each other, they're the same,
they go away.
They cancel each other out.
Another way to kind of think about what Mrs. Stevenson has just done is this is a new trick that you can put in your algebra pocket to help solve a problem. Instead of adding or subtracting numbers on both sides or square rooting both sides, you can now take a logarithm as long as you do it on both sides with the same base.
Right. So on the right side, we are just left with the exponent, which was X plus Y. The left side of our equation looks like the left side of what we were trying to prove. And the right side, X plus Y, is
what we
log
said.
B R and log B S. So let's just finish substituting in. So log B R plus log B S. And that's not necessarily a straightforward proof. It's not really anything like the trig identity proofs that we
But that's why it works.
But that's why it works, and you could do something similar for these other two properties as well to be able to prove that.
The other thing I wanted to point out here also is when Mrs. Stevenson took the log of both sides, you could just as easily have said that a logarithm is equal to its exponent. And so
that's true.
You could have gone right from blue to the purple with the log base B. That's your base.
I tend to forget about that step there,
and it equals the exponent. Well, my exponent was X plus Y. So both of those are totally legitimate ways to do this. It just depends on what your brain sees. And we obviously see things the same, but a little bit differently.
Yes, totally. Okay.